More time. Start again. How can sports science assist athletes and coaches in making the right decisions within a race, during the race, before the race? I'll try to speak up a little bit more. How can sports science assist athletes and coaches in making the right decisions during the race, before the race? What kind of decisions are important for sports sciences? And then mainly also during the race, pacing strategies. I will be chairing this session. I'm Florentina Hettinga from the University of Essex, and also introduce the topic pacing. There's not just one way to go to you. Then my colleague and friend Bert Otten will give a lecture about how modeling can assist cyclists in making decisions. And Dr. Mauger from the University of Kent will talk about how pain can be assistive in making decisions during the race to pace yourself. First, I'd like to start off with introducing the concept of pacing a little bit more, and as we scientists always do, look back into literature, what has been published about pacing already. I had to go way back, as you see, because 2,500 years ago there already was a story about pacing in literature. The little fable about the tortoise and the hare. There were a hare and a tortoise, and of course the hare was way faster than the tortoise could ever be, and the hare was also, of course, nagging the poor tortoise about being so slow and that he could never ever beat him during a one-to-one competition. Well, said the tortoise, okay, let's do that competition then we'll see who wins. So, well, they started, and they did their time trial basically, and this tortoise won because the hare thought, ah well, I'll win anyway, so I can have a little nap along the side. It's so warm, it's so hot, so well, I'll have a little rest. And in the meantime the tortoise, well, not quickly but slowly moved along and won. Now you would say, well, that is a nice story, but it's a little bit of a fable, so it's not real. What does this have to do with sports science? Well, if you look at the sports of today, you might remember this athlete, an Australian athlete, short track athlete, Bradbury. And actually he relived kind of the story of the tortoise and the hare in the Winter Olympics in 2002. I'm not sure if you remember this athlete, but what happened to him was that he was competing in the finals, but beforehand he already knew, I'm not good enough, I'll not be the winner of this race. But well, maybe the other competitors will fall during the race, because yeah, short track it's always a little bit crowded and many athletes fall. So he waited a little bit, and indeed in the last lap all the other athletes fell and he became Olympic champion. So he's a bit of the tortoise in sports sciences, while the hares all fell down. So still, pacing is important in sports sciences, and it is not only important to be strong, but also to be smart. You have to pace your race in the right way, and you do not have to make any mistakes, because if you make a mistake, you'll lose the competition due to bad pacing, or in a broader context, bad decisions. So you have to be strong, but also be smart. As Ross Tucker already told this morning, a lot of research has been done on pacing and fatigue. In 1996, so that's almost 2,500 years after the first literature on pacing, science started to pay a lot of attention to it again. Teleoanticipation was introduced. There must be a feedback control system including a programmer that takes into account where the endpoint is, so that we can adequately pace our race A central governor might be present that regulates all of that, because for scientists it's always important, of course, to think about how pacing works. What is it? What does it? How does it work? So this was the first scientific literature that started to try to unravel these concepts, the concept of pacing and how it works. That inspired a lot of scientists, and recently, in the last year, 3 very interesting literature reviews on how pacing works are published. The first one looks at it from an ecological psychology perspective. That means that it takes into account the environment, because a central programmer and things like that is something within the athletes, but it doesn't explain how an athlete responds to the environment yet, which is very important because there are opponents, there are different circumstances. So this theory takes that into account. Then there's the heuristics, a paper that applies decision-making theory and thinks about pacing from a heuristic point of view. Actually a kind of systematic problem-solving way. And the last one, as Ross also mentioned already, neurophysiology and neurotransmitters in the brain are important, influencing motivation, drive and things like that. So there's a lot going on understanding the process of pacing. But we're here for the Tour de France, of course, so it's not only about developing a theoretical understanding, but also about how to apply all these knowledge. And literature on pacing has focused on largely 3 things, but mainly on this one, time trial exercise. But if we look at the Tour de France, there are most of the stages are not time trials, but also involving competitors and multi-stage events. So it's more complex than only time trials. What we do see in the mentioned paper is that also in the Grand Tours you see a process of distributing energy during the whole event. So you pace yourself not only during the race, but also during the weeks of exercise that you need to do. And very recently scientists are also starting to focus on understanding the opponents in the whole story, not only focusing on how to pace yourself in time trial exercise, as Ross has explained about already, but also how about competitors. And tomorrow at the European Conference of Sports Science there will be at least one lecture about that. As I know, many of you are pacing themselves through all the very interesting conferences that are going around this week. So if you happen to be in Amsterdam, have a look at this lecture tomorrow. But back to pacing and the different approaches, because that's actually something I want to talk about today, and that also my fellow presenters will be talking about. There are many ways to study pacing. Some of the previous presenters have mentioned that it is important to integrate a lot of theories and aspects, and I think that is very important because pacing is a complex thing with multiple aspects that are involved. So to start, an example of taking a modeling approach to understand pacing strategies, and that is by using a biomechanical approach, modeling an energy flow model, so modeling an athlete by modeling the flow of energy, a biomechanical approach. Started by Gerrit-Jan van Inge Schenau in the 80s already, and this principle, the law of conservation of energy, is important in modeling an athlete according to an energy flow model. I have to look at the time to see if I'll show this little movie that explains that basic principle. I think it's better to skip this one out for now, but here's the link. It's nice to see it's a professor from Harvard that explains the basics on the law of conservation of energy, so have a look at that. I'll focus on how to apply that to an athlete. If we have an athlete cycling or skating, but let's focus on the cycling one, it is important that he generates energy. He needs his muscles to generate energy. So that's what he is doing here. He produces energy. He needs that energy to overcome frictional losses to the air friction, or to the ground, rolling resistance. And also he needs, of course, to accelerate or decelerate, and there is a velocity, a kinetic energy component. So with all these components, an athlete can be modeled. And if we have that model, we can apply that to pacing in speed skating and cycling. Because we can simulate performance now. Instead of having an athlete experimentally cycle a lot of trials, we can say, well, we model that athlete and we have cycled him 1,000 different velocity profiles, 1,000 different pacing strategies, and we can see what his final time will be. So that's a way to help coaches and athletes to understand what the best outcome of the race will be. Should we start like this, fast start, or should we start like that? Well, as the arrow might give away, the fast start strategy appears to be the best. For a 1500 meters it is based on speed skating data, but also for if you have to cycle a 1500 meters it is. Based on this model, generally we can say if you have an exercise that lasts 2 minutes, shorter than 2 minutes, an all-out strategy is best. If it's longer, an even pace strategy is best. And for a 1500 meter, which is important in skating, it seems like athletes should start a little bit faster than they usually do, but it is a bit more difficult because it's on the border of the two. And if we test that, we see that the predictions of the model seem to be the same as if we actually have some athletes cycle a time trial multiple times. Then we also see that the best performances are associated with the fastest start if we go for a short time trial, so 1500 meters, 2 kilometers. With speed skaters it's a bit more difficult because they seem further away from their optimum, and that might be because small variations in pacing appear to have very, very large consequences on their technical ability. And that led to a different study, because first we looked at how modeling can assist sports sciences, and we could model different pacing strategies and advise what would be the best strategy and what would be a strategy to test with. But there are some things not involved in the model, such as fatigue, technique, pain, what Lex will also be talking about, motivation, the opponent, what I already discussed. So there are also a lot of things that need to be further understood before we can model the whole thing. And that is where maybe a comparison between cycling and speed skating can be important for. Because there are similarities between the sports, but also differences, mainly related to technical ability, postural control, because this is the skater has to maintain this crouched position, and coordinative aspects. So it might be interesting to look at differences between these two sports. And that's also something I would like to show you some results of, and that is if we have skaters and cyclists have perform their sport of expertise for a 1500 meter, and we give them the same instruction. One is start slow and one is start fast for both of them. So they both cycle 2 trials or skate 2 trials depending on what they are. Then we see that different strategies, they have different velocity profiles if you give them the same instruction. So in this picture, the speed skaters are presented, and what we see here is that their fast start and their slow start are relatively close together. If we look at the cyclists, we see that their fast start is very, very, very explosive. So with the same instructions, do a fast start, they go out way faster than the speed skaters do. So the cyclists seem more explosive, while the skaters, they stretch their start more over 700 meters. So it seems that indeed there are differences in pacing, even though the instructions were the same. At the same time, we measured fatigue aspects of these skaters and cyclists, and what we saw is that I'll move on to the results, that both peripheral and central fatigue were important in this exercise. We didn't see any differences between the sports. We didn't have many subjects, but we're still thinking a bit how to interpret that. But what we did see was that speed skaters seem to be more conservative in pacing, possibly because they anticipate a greater amount of fatigue and homeostatic disturbance, and they do not want to have that negatively impact on their performance. So sports, fatigue and technique seem to be related. What I would like to show with these two examples, the modeling but also the fatigue studies, is that it is important to look into pacing and optimizing pacing from various angles. There's not just one way to go. There are multiple components involved, and a lot of this interact as well. And that's also why I think that the different approaches should be taken to assist coaches and athletes in making their choices. How to pace their race during the race, but also, like Bert will be telling about, how to choose which bike they should ride. That's something where modeling can be assistive of how pain can be used to pace, as Lex will be telling about. So with this I would like to invite the next speaker, Professor Bert Otten from the University of Groningen, to present the research on the modeling.
Thank you.
And how modeling can be assistive in sport science and in making adequate decisions.
Thanks very much, Floor. How much time do I got?
20 minutes.
Really?
Yeah.
Oh, okay. Let's do it. I'll give you a talk about simulation of time trials. It all started a while ago with simulating Teun Mulder, who's a Dutch track cyclist on 1,000 meter. We had very accurate data. Albert Smith is around here who offered the data. You can see the velocity over the race, which is less than 1 minute, and the red curve is the simulation. So that looks pretty accurate, but how did I get to that? First, I'd like to indicate if you've got a model, you can change all kinds of things, like the gearing, which is very nice, because then you can simulate with different gearings what will happen. This is the power output measured, is the green curve, and the other ones are two power curves calculated. Now the point with cycling is that it's different from normal power production by skeletal muscle. If you've got a skeletal muscle, power production depends on the velocity of shortening. And it's a famous hill-like curve like this. But in cycling it appears, and it's very interesting to try and explain that, which is shown in this paper, that the power pedaling rate curve is not curved but it's linear, which makes life very simple. You just need to know the max RPM of a cyclist and the static torque that he can produce, and then you got a straight line. So it's very easy to model. So the RPM and power relationship can easily be modeled for one cyclist. Now on top of that, you can simulate power production by various reserves in the body, anaerobic, aerobic, and a tap, and this can all be fitted. So that's where I was with track cycling. And then all of a sudden these people came along. They are from Top Sport Topics, and they said, listen, the guys at Belkin have a problem. Mathieu Heijboer, I think he's around here, asked the question, we want to have a stage in the Giro d'Italia, and it's not clear what bicycle to pick. Should it be a light bicycle or an aerodynamic bicycle? And I said, well, if you got the data, I can try to model it and see what goes on. And so this was the guy I had the data from, Steph Clement, a very good time trial cyclist, and I did the simulations, and this was the result. He didn't win, because this is Alex Dowsett, a British guy, and Steph came in 5th, which was very good for what he did. So I was pleased. Now how did I do it? The point was I needed a lot of factors. On top of the track, you need to know the whole three-dimensional shape of the stage, of the road. Now you can measure that quite easily nowadays. You need to know rolling resistance, the mass of the rider and the bike, it's all known. You need to know wind direction, that's a problem. You don't know the wind direction at that day. You need to know the power that the cyclist can deliver, that's quite well known. You can measure that. Then the power RPM relation, I showed that. The critical angle of the bikes in the curves. I measured that in many videos, what the critical angle is before a cyclist starts to fall. And the time needed for braking. How much time do you take to stop pedaling before you reach a curve? What kind of gears are present? We know that. How much time do you need to change gears? It's not infinitely short. A computer can do it much faster than a human being, but you need to do it right. What's the temperature? What's the air pressure? All these things are there. Now just to you know all this, the frontal surface of a cyclist is very important for the aerodynamic drag, so you need to know that. All this stuff was measured in the velodrome in Apeldoorn by the team, and we knew the data on several different bicycles with different riders in different positions, so that was nice. And it appeared that Steph Clement had a frontal surface area, effective CDA, so the dynamic coefficient times the frontal surface, is only a square meter, a quarter of a square meter. That's just this thing he needs to drag through the air. That's wonderful. He's not so big, but that's still fantastic. Now rolling resistance is quite easy nowadays, and so we got GPS data of important time trials in the 2013 races. This is Ambron Gorge, that's the elevation, and we got a lot of data from the power output they actually could deliver. Critical angle, It's about 30 degrees on a dry road. Beyond that it becomes difficult. If it's wet, 20 degrees, roughly. It takes about 5 seconds for people to stop to decrease velocity. Downhill it's a bit longer. And so we did the simulation. This was the stage. It was a hilly stage, the northern coast of Italy, and the hills were not all that big. And that's why they asked the question, do we need a time trial bicycle or a light normal bicycle? I did the simulations and it appeared to be that the time trial bicycle was best. It saved them about 19 seconds, and then in the evening I saw that my simulation was 0.03 kilometers an hour off the real velocity he rode. And I thought, that's crazy. I must be so lucky. You can't do that. I mean, 36 kilometers an hour, that's a small difference. And so I thought, well, I must be lucky. Then I did a simulation of another one, the Tour de Suisse. There we had to change bicycles. And everybody knows where. There. That's not difficult, right? And you can calculate what the difference is in seconds. This is Bauke Mollema, one of our great riders, and I was 0.05 kilometers wrong. I thought, well, I'm lucky again. Then we did a flat time trial of the Tour de France, 54 kilometers an hour on average, with the wind in this direction, and quite flat, as you see, just 100 meters. This is Bauke Mollema again, and I was 0.1 kilometers an hour wrong on a completely different stage. Then I thought, maybe it's not such a bad model. And then we did this one, Ambro Gorge, and that's fun, because there you can change bicycles. And what I did, I asked the model to simulate it on every 10 meters to change bicycles. And it appeared that you have to do it there. And all the big teams were changing there. And all the camera crews were there. And they said, Belkin must be out of their minds because they're not changing bicycles. Right? They're just zipping by. They already had changed bicycles. I had a good time. This is the velocity profile. And this is what I give them. How did I take care of the wind direction? Well, I just simulated all directions with all speeds and calculated the difference between the bicycles. So they could select in the morning what bicycle to take. Right? And that's Bauke again. So it looked pretty dramatic. This model was really working. And I hit the newspapers, because I had published it 1 week before the expected average, and I was 0.1 kilometers an hour off. And so they were pretty happy. The point here is that the average speed to predict is not really the most important thing. I mean, that's fun, to be able to be close to what actually happened. That's fun. But if a rider doesn't have a very good day, he might be slower, right? But he will be slower on both bicycles. So the prediction or the statement, you should take that bicycle, is much more robust than the statement, he's going to do 35.6 kilometers an hour. And that's important to keep in mind. So the difference in time using different bikes is much more robust against circumstantial variations than the final time itself. And these examples show the use of these simulations for the cycling sport, in particular time trials, because it can be really helpful. If you've got a small difference in wheels or in frame weight or etc., you can actually try that. It's very hard to do it in real life because a rider is not fantastically constant, so constant as a computer could be. Now, I must state that this is only extra information. As a scientist, you should always be very humble. Never claim that you know what the situation is for a rider 100%. There are many factors. There are many factors. If a rider or a coach says, I find one other factor much more important, the color of the frame or whatever, it might be crucial. there are so many factors that are not in my model. Psychological factors, for instance. I'm assuming that this athlete can produce what he has produced in a measurement during that time trial. Might not be true, might depending on other factors. So let's not say that we know it all, but let's say we've got a new tool with which we can see what happens if you change things like gearing or like the weight of the bicycle, etc. Now, this is what happened with biomonomer at the last stage that I calculated. Now, if you look at it, it's very interesting because it's got a couple of aspects. First of all, it took him just a few seconds off the real time. It cost him a few seconds. Secondly, he was hanging into the curve and had selected a certain speed, but he couldn't handle it. So he chose to sort of rub with his shoulder against the boarding to stay on his bicycle rather than to slip away. I find that very interesting. He made a short decision and it worked. May not have been the right decision, but that's an interesting process. People see optical flow, they feel all kinds of things, and on the basis of a short moment in time they make a decision. That's what makes a cyclist a good one or not. Now let's take a short look at the future. I want to put more into the model, especially power production was not assumed to be independent of air pressure, and Florentina knows better, so I need to adjust that. I want to refine the physiological model, and I want to have better simulations of shielding, so I'm already working on that to simulate group time trials, because that's of course shielding from different cyclists, and that's a very nice thing to do in a computer, and to get the right order of the cyclist and the right timing from which to change. They might not be the same for everybody. So that's a very exciting field that we're entering right now. Thanks very much for your attention.
Okay, thank you, Bert, for your great talk. We'll save the questions for the end of the session because we might be tight on time schedule. So I would first like to start with introducing Dr. Lex Mauger from the University of Kent to start about how you can use pain to pace.
Okay, thank you. I've got the good fortune of going last in this symposium because it means that some of the concepts of pacing have already been mentioned by Bert and Florentina. So that gives me a bit more time to concentrate on the main focus of my presentation, which is the idea that pain influences the way we pace ourselves. So although some of these concepts of pacing have already been discussed today, certainly by Ross Tucker but also by Florentina as well, I think it's still important that I provide a bit of an overview of some of the key aspects of pacing, because they might, I think they're going to be important for understanding this relationship with pain and performance. So over the talk I'm going to provide a bit of a summary of pacing and then draw out some of our current understanding for how we pace and what our pacing-based behaviour is. I'll then go on to talk more about pain and discuss why it is that we feel pain during exercise, and then theorise how it is we might use that pain to pace ourselves. I'll present some of the limited literature in the area and then conclude some of those study findings to present an overall case for the pain, or the role of pain, in pacing exercise. So I'd like to start with a little bit of a subtext before I get into the real parts of the presentation. And the subtext is understanding the difference between task cessation, fatigue, and performance. Now, fatigue has traditionally been measured through time to exhaustion tests or repeated maximal voluntary contractions, and classic fatigue is said to occur when someone can't maintain the required force or they stop exercising altogether in a time to exhaustion task. Now, for me, this isn't really a true measure of endurance performance, because certainly there's no Olympic event that requires somebody to maintain a fixed intensity for as long as they possibly can. So instead, I believe that a time trial type model, where someone has to complete a fixed distance as fast as they can, is the true measure of endurance performance. Now, if we apply the traditional idea of fatigue to this time trial based model, then it would be suggested that any time the person reduces their work rate, then they've fatigued, and we know this clearly isn't the case. This reduction in work rate at the start and towards the middle of a time trial is purely a pacing based decision. So it's my understanding that in pacing, this true fatigue never really occurs at all. And instead, pacing is all about trying to regulate this rate of fatigue. So we're never terminally compromising the exercise until we reach that finish line. Unless, of course, there's some sort of serious error of misjudgment in the athlete. So if that's the case, pacing is essentially all about the intelligent regulation of fatigue by changing our work rate or power output over the exercise so that we ultimately produce our optimal performance. Now, in order to do this, we need to have knowledge of the task, we need to know what it is that we're going to be doing, we need to have an idea of the physiological capacity of the body, what it is that we're capable of, and we also need to know about the relative rate of fatigue during the exercise as well. If we're missing any one of those concepts, then ultimately performance is going to be compromised, or we're not going to be able to finish the event at all. So based on this, our current understanding of pacing, or at least my understanding of pacing, is that a pacing strategy is preset prior to exercise, based on the endpoint, or the knowledge of the endpoint of the exercise. And this creates an initial pacing strategy or pacing schema. During exercise, distance feedback or continual distance feedback helps reinforce that knowledge of the endpoint, so it might strengthen that pacing strategy. And if we have prior experience of the exercise, that's going to be further strengthened as well. But we need continual feedback during the exercise, both from afferents but also things like environment as well, which will also help recalculate that pacing strategy so that ultimately we're going to produce that optimal performance. So essentially, this pacing strategy is a continuous and continual comparison between our expectations of the exercise based on the prior experience that we have and our knowledge of things like the course topography and the climatic temperature against the relative physiological demands of the exercise, what our body is experiencing, and that investment of energy over the course of a race. Now, it could be suggested that endurance performance, as Ross Tucker mentioned earlier today, has already been well explained by Joyner and Coyle's model of endurance performance, where maximum oxygen uptake, lactate threshold, and gross mechanical efficiency combine to basically produce our overall race pace. Now, whilst I think this model is extremely important and can well describe the majority of endurance performance, there's a number of things which it can't explain. So firstly, it's unable to explain how we have some inherent variability in our performance. It would suggest that every time we perform a time trial or an exercise, we would produce exactly the same time on each occasion, and we know that's not the case, and it's a pretty good job that doesn't happen, because sport would be no fun if that was the case. Secondly, it doesn't explain how an individual with no real experience of the exercise, and also no external feedback based on speed or power, is able to produce something pretty close to their optimal pacing strategy based only on their feelings and perceptions. So there has to be something going on here which allows the body to sense exactly what's going on here, so that they're able to regulate their work rate in this intelligent manner without any external feedback at all. Finally, it doesn't suggest, or it doesn't explain how manipulations or interventions which don't affect any of these physiological parameters are able to improve exercise performance. So some of the psychological interventions that Sam Marcora mentioned earlier today are able to improve endurance performance, and this model can't account for that. Now, one of the concepts of pacing which I didn't mention earlier is this idea of a protected metabolic reserve during exercise. So this is the idea that our true physiological capacity or capability of a body is never really reached during exercise. We've always got this metabolic reserve which we don't really tap into. And pacing is all about trying to maintain this metabolic reserve by this protective threshold. Now, in some cases, or through some interventions, we might be able to push into this protective threshold. So maybe with some of those psychological interventions, maybe with high levels of motivation, we can push closer to this. But essentially, the pacing strategy is all about regulating this reserve at the end of exercise. So, whilst I suggest that endurance performance is largely explained by this particular model, I don't think it explains this concept of the metabolic reserve, and it certainly doesn't explain how it is that someone can effectively produce an excellent, close to optimal pacing strategy in the absence of any sort of feedback at all. If you get someone to do a 10-mile race, then they can pretty much work their pacing strategy to as close as optimal as possible. So what is it that explains these perceptions and feelings during exercise? Now, many people would suggest the RPE scale is a good marker of this. The RPE scale describes the effort invested in the exercise, ranges from a 6 to a 20. Now, whilst the role of RPE in endurance performance has a lot of data supporting it, and certainly Sam provided a good case for it earlier today, And I wouldn't disagree with a lot of this data. I think it has a certain amount of importance in endurance performance. But I don't think it explains all of it. My biggest issue with the RPE scale is it's essentially a made-up scale by sports scientists. If you ask someone who's not in the exercise profession, who's not a sports scientist, they probably haven't ever come across the scale before, and if you ask them to explain their RPE, they wouldn't be able to do that. So it's not universally recognised outside of a sports science lab or for someone who hasn't seen the scale before. Even when you go and speak to a sports scientist, depending on which lab you go to, you'll see a different set of instructions or different descriptors which might range from any one of the following depending on which lab you're in. So even the sports scientists can't agree what RPE actually is. So we can see a bit of a problem when it's used to describe endurance performance, from my perspective. If we compare this, on the other hand, to pain, for example. So pain is universally recognised. Anyone knows what pain is. It's fairly easy to describe, and it's easy to report as well. We also know that pain is ultimately a warning sign for impending tissue damage. So it must provide a powerful drive for us to change our behaviour. And if we understand pacing as a decision-making process, and if we can reduce our pain by reducing our work rate, then surely pain has some grounding for making pacing-based decisions, because it is a powerful drive to effectively protect us from going into this metabolic reserve. So I'm going to talk a little bit about pain in some more detail now, but before I do that, I'm not saying I disregard anything to do with RPE or any of the joint and coil model. I see pacing as a hugely complex process, and exercise-induced pain merely is one of the multiple facets of this. So I believe exercise-induced pain is important for exercise performance, not so, or not as important as any other aspects. It's just largely been disregarded or not had enough attention within the literature. So the causes of exercise-induced pain during performance is said to arise from one or any combination of an increase in intramuscular pressure, a release of noxious biochemicals within the muscle, or a distortion in the tissue associated with muscular contraction. Now, the most popular of these is said to be this release of biochemicals, these deleterious metabolites, which is said to either activate or sensitize these type 3 and 4 afferents, which are located in and around the muscle. So these 3 and 4 afferents basically sense these metabolites. They transmit this nociceptive, this painful signal to the spinal cord, where it's relayed to the brain and ultimately processed as pain. Now you can see how this is tightly bound to work rate as well, because these metabolites are released when there's a disturbance to homeostasis, and we know that with increases in work rate we get a greater disturbance to homeostasis. Therefore increases in power output should increase the sensitization and firing of these afferents, which will ultimately lead to an increase in pain for a given level of work rate. And if we look at the literature on this, that's exactly what we see. So it's suggested that exercise-induced pain begins at approximately at an intensity equivalent to 50% of the VO2 max, and increases fairly linearly alongside exercise intensity and metabolic demand. So the harder we work, the more pain we're in. Now interestingly, data from our lab as well suggests that the willingness for someone to engage in exercise-induced pain during self-paced exercise to exhaustion is very well correlated with time trial performance. Now this suggests that someone's tolerance to exercise-induced pain is possibly a good predictor of their exercise endurance performance. Now I mentioned about the joiner and coil model not being able to necessarily explain why there's some variation in performance. But if we look at pain, pain is ultimately a subjective measure, and we don't always feel the same pain for a given signal. So it depends very much on circumstances and the situation we're in. So for the same type of exercise we might feel more or less pain depending on things like task familiarity and motivation. So this difference in pain for the same sort of exercise might also help explain why we see variation in performance when some of these physiological constructs are ultimately fixed. Now whilst we can control and account for some of these variables such as motivation and task familiarity, actually trying to experimentally measure experimental pain during exercise is fraught with difficulty. We can approach it from two different angles. We can either look to increase pain during exercise and see what happens, or we can look to decrease pain during exercise. Now, part of the problem with this is it's going to induce a series of side effects which might ultimately compromise exercise performance as well. So one of the most important of these is the exercise pressor reflex. So not only do type 3 and 4 afferents transmit that painful signal to the brain, but these afferents are also responsible for controlling the cardiovascular system as well, or providing information for cardiovascular control. So by manipulating pain, we also change how the cardiovascular system responds to exercise, and that can have implications for exercise performance, which means teasing out some of the role of pain is particularly difficult. Part of the other issue as well is that different types of pain are sensed and processed very differently in the body. So we respond very differently to thermal pain, chemical pain, pressure pain, and all of these are perceived in a very different way. And this might explain why data from our lab we've shown good correlations between exercise-induced pain and endurance performance, whereas classical measures of experimental pain, so pain tolerance through a cold pressor test and pain pressure thresholds through algometry, have pretty much no correlation between endurance performance. So it's not an easy thing to study in exercise, which might explain why there's a relatively small pool of experimental studies which look specifically at pain and exercise. Unfortunately, not only is there a small experimental pool of this, but a lot of these studies haven't been well designed, and so our knowledge of this is very much speculative. So I'm going to introduce a few of some of the better papers in this area, and then make some conclusions based on these. So these first couple of studies have used a paradigm where they're looking to increase pain during exercise. And in this particular study, they used naloxone, which is an opioid antagonist. Effectively, it means you feel more pain for a given stimulus. And what they did is they infused that during a time to exhaustion exercise. And they found that with subjects who had had the naloxone infused, they actually had a reduced time to exhaustion here. So it appeared that increased pain during time to exhaustion reduced their exercise capacity. Now, in support of this, in another study, these researchers used hypertonic saline solution injected into the muscle, and that causes a kind of burning, cramping muscle pain, which is similar to exercise-induced pain. And they did that during maximal voluntary contractions, and they found that in the higher pain condition, MVCs were reduced. So in not all studies, but most studies which seek to increase pain during exercise, there appears to be a reduction in capacity or a reduction in performance during exercise. Now if we look at the other side of the coin here and we see what happens in studies which seek to reduce pain during exercise, and some of the data from this has come from our labs again. We used an acute oral dose of paracetamol prior to time trial cycling performance, and we found that cyclists in the paracetamol condition were able to maintain a higher power output through the exercise, which resulted in a significantly faster time trial completion time. In a follow-up studies of this, we repeated pretty much the same protocol, but did it in repeated sprint exercise, and we found that those participants in the paracetamol condition were able to produce higher power outputs in the last few sprints. So we speculated in these studies that the cyclists were willing to engage in a given level of pain during the exercise and would help control or moderate that by changing their work rate. So by giving them this mild analgesic, they would feel less pain for a given power output, so instead they could raise their power and therefore produce an overall better performance in this analgesic condition. Now, although the data on these analgesic studies is relatively new, it appears that athletes and competitors are pretty well versed in the benefits of analgesia during exercise, because certainly if you look at the incidence of use of analgesics in competitors, it's pretty shockingly high in a variety of sports. And we can perhaps see why in this. In this particular study, this was for users of paracetamol. In regional and national athletes, there was a higher incidence of use from their non-athletic controls. And for those athletes that did use paracetamol, their rating of perceived exertion at an intensity equivalent to their lactate threshold was significantly less than their non-paracetamol counterparts. So it appears that athletes are aware of the benefits to this as well. And it's also, of course, not just our analgesic drugs that we see as analgesics. If we look at the most popular, probably ergogenic aid in sports performance, so that's caffeine, most of us would see this as a stimulant. What a lot of us don't realise is that it's also a mild analgesic. So following ingestion of caffeine, we actually feel less muscle pain for the given exercise intensity. So it might be that actually caffeine's ergogenic mechanisms might be explained by this reduction in pain as well as its stimulant properties as well. So again, although the literature is fairly sparse on this, in the majority of studies which seek to reduce pain during exercise, the general finding seems to be that a decrease in pain improves exercise performance. But we can go to the other end of the scale here as well and see what happens when we remove all pain during exercise. And this is probably a figure you've already seen today in Ross Tucker's talk. Because in Marcus and Mann's study, where they used fentanyl to remove all type 3 and 4 afferent during time trial cycling exercise, it wasn't actually their intention to remove pain, but because they blocked all afferent feedback, the removal of pain was a consequence of their intervention. So we can see in the two control conditions here, we see a fairly standard parabolic pacing strategy: initial fast start, plateaus off in the middle, and then an end sprint towards a final kilometre or so. If we look at the fentanyl condition, where no pain is present, we see pretty much a complete positive pacing strategy, almost an all-out pacing strategy, which is clearly not appropriate for a 4-kilometre cycling time trial. So it comes as no surprise that by the middle of the exercise, they had a significantly higher blood lactate concentration. Performance was compromised in the second half of the trial. By the end of the exercise, they had induced a significantly higher level of peripheral fatigue, which was associated with ambulatory problems for up to 2 days after the exercise as well. So it looks as though these athletes, in the absence of pain, were able to access that metabolic demand to such a degree that their ability to even move over the next couple of days may have actually been compromised. So it seems that protective threshold maybe does serve some purpose. So my understanding of pain, based on the literature, is that exercise-induced pain is a useful signal during exercise, because ultimately it provides a window for us to understand the relative demand that's been placed on the muscle and our relative rate of fatigue. Now, if we remove all pain during exercise, then this has negative consequences because it affects our ability to pace, which is clearly evident in this study. However, because pain is likely to serve some kind of protective function by preventing us from going into metabolic demand and metabolic reserve, and because this protective threshold is set probably at a conservative level, if we have mild analgesia which allows us to push slightly into that metabolic reserve, it might be that we see these small improvements in performance. So I'd like to close just as a bit of a caveat to some of the data that I presented here, and say, whilst I've presented data which suggests that mild analgesia might improve exercise performance, I certainly wouldn't advocate the use of analgesics during sports performance. All of these analgesics have been administered in controlled lab safe settings with ethical approval, and using them in competition or even in practice is potentially dangerous, even if we're not mentioning some of those ethical concerns associated with this essentially drug abuse. So what I would suggest that athletes and competitors do is accept that exercise-induced pain is part and parcel of training and competition. It's something we need to accept that happens and not look to try and remove it altogether from exercise. So we should look to maybe embrace it, learn to overcome it, and the masochists amongst us maybe even learn to love it as well. Thank you very much.
Thank you, Lex, and thank you, Bert. Would you please come up here to address some questions that might be there? The floor is now open for questions. Go ahead.
I'm interested that you're wary of recommending people take paracetamol, but we often recommend carbohydrate when that can end up with vomiting and diarrhea on the side of the road.
Yeah, I mean, I think the use of analgesics probably has more serious consequences than just vomiting and diarrhea as well. I think paracetamol's, I think I'm right in saying that it's the biggest cause of liver failure in the US and the UK as a result of overdose. It's actually one of the safer analgesics out there, but it appears the incidence of use of analgesia in sports is actually more down the line of non-steroidal anti-inflammatories, things like ibuprofen and diclofenac, and they have much more serious consequences for not even overdose, but during things like dehydration in combination with carbohydrates. So they can cause something called exercise-induced endotoxemia, so it affects the mucosal lining of the gut. That can cause kind of bacterial leakage into the intestine, and as a best-case scenario, vomiting and diarrhea. As a worst-case scenario, sepsis and hospitalisation. So I think kind of looking at the sort of safety profile of these, I wouldn't recommend it based on some of these pretty shocking.
It's kind of a thin end of the wedge thing, that people are never going to just take a 1 or 2.
Yeah, exactly, and it's not just taking 1 or 2; it's the cocktail that's being taken alongside of it. So someone might be taking paracetamol, ibuprofen, caffeine, taking a hard dose of carbohydrates alongside salt tablets. You're taking a mix of drugs, but we're not really sure what's going to happen combined with exercise. So it's not a practice that I'd advocate at all.